In section 3.4, we're going to learn how some of the calculus stuff we've been learning about derivatives relates to physics, including velocity and some other rates of change. If you recall, instantaneous rate of change is that moment when that vehicle passes by and we measure how fast it was going at that moment in time. And if you recall, we used, earlier in the chapter, we used the formula shown here, which is the definition of the derivative. Well, now we have a shortcut for finding the derivative, and then we can run a through the derivative, and that's going to tell us the instantaneous rate of change. It's the value of the derivative at a point. So if they ever ask you for the instantaneous rate of change, you can just find the derivative and then run a right through it. Much of calculus involves a discussion of how things change over time, changing things. So for example, here we have a circle, and imagine if its radius was slowly growing. Well, what else would grow? Well, you might be thinking, well, the diameter would be growing too. But what else? How about the area would be growing? And it would be growing at a different rate because area, is a function of the radius. There's a formula there. Of course, the circumference would be growing at yet a different rate. So there's several things that are related here. They're all related to radius. And we could figure out how fast the area is changing with respect to radius. So let's do that. Let's start with the area formula of a circle. Do you recall that it is A equals pi r squared? Now I want to remind you that A is area and it's a function of radius. So the independent variable here is radius. We choose the radius. The radius is going to be changing, in fact. And then it causes, think of it as causing the area to also change. Well, you know what? We can take the derivative of this function, a prime of r, would be. Now, let's think about this. We don't have to do the product rule here, even though we do have a product, pi times r squared. Why don't we have to do the product rule? The answer is because pi is just a number. This is kind of like saying 3.14 r squared or 3r squared. You just throw the 2 out front and multiply by pi. The base stays the same on the independent variable and reduce the exponent by 1. That's the derivative. This is another way to change it, or write it. The derivative of area with respect to radius, where radius is the independent variable, so 2 pi r. So find the rate of change of the area of a circle with respect to radius. Now let's think about this for a minute. As radius changes, so does the area. But the bigger radius gets, the bigger the change in area, because think about this right here. If we add another centimeter onto this, we're going to add some area. But way out here, if we add a centimeter, we're actually going to add extra area, or more area than we did here. So the amount of area that's growing or adding with 1 centimeter change, that amount is changing too. It's not fixed. Like every time we go out a centimeter, we don't just add 5 square centimeters. If we go out at a centimeter here, we might add 6. And then a centimeter here, we might add 7, and so on. So the amount of change is actually growing, which is why we have a function that tells us the amount of change at a certain size of circle. All right, let's move on. So on the previous slide, we figured out that the area was changing with respect to radius at a rate of 2 pi times the radius. So now we could figure out how fast was the area changing the moment the radius was at 5. The moment the radius was at 5, how fast was the area changing? So we do dA dr equals 2 pi times 5, which is 10 times pi. 10 pi, or 31 and 31 units here. All right, or we could then do dA dr equals 2 pi. Well, how about later when the radius was as big as 10? how fast was the area changing at that moment, it would be 20 pi units here. All right, let's move to the next slide where we're going to talk about the units. What would the units be? Let's assume radius was centimeters, okay? And then let's assume, of course, area would be square centimeters. Well, this is the change. dA represents the delta, the change in area. So we would have, the units would be square centimeters of area per centimeter change of radius. So every time the radius changes by a centimeter, the area would go up by centimeters squared. Okay, and of course that amount changes where you are at the circle. In this course, we're going to be working with motion. One of the examples of motion could be just motion along a number line. So for example, we might have a number line, and then you have an object. We'll call it a bouncing ball. This bouncing ball is bouncing on the number line. Okay, and we can record all the information about where it was at any given time. Time is going to be your independent variable. It's going to be the thing on the inside of the function. And the function itself, remember the outputs of the function are going to tell you where the object was. So at time 0, maybe I'm at 3. And then at time 1, maybe I'm at 2. So 1 would be the t, and 2 would be the s, or the f of t. We're going to use the letter s to represent position, where it was in any given time, position. So we're going to be moving an object along a number line. All right, now there's another term on the board here, displacement. Here's another vocabulary for you. The displacement of an object would be the net change in position. The net change in position. What does net mean? Net means after all is said and done, where are you? What was the change in position? So for example, let's say at time 0 I'm at 1. And then I bounce around for like 10 seconds, and I end up at 0. Okay, so I started at 1, I bounced around for 10 seconds, and then ended up at 0. What was my displacement? Well, I started here and I moved to here in the end, so my displacement would be -1. It's my starting position minus my ending position. Ending, I guess I should write the letter S there, ending position. So my change in position was I moved to the left by 1, so that's called displacement of -1. It didn't matter how far I traveled, it was simply the displacement, just how much I went to the left or to the right. And in the end, I went to the left by 1. Another term you need to juggle in your head. A lot of vocabulary in this section. Average velocity. Average velocity. Well, you know what velocity is. It's like 55 miles per hour. That's a rate or a velocity. Well, what is your average? Well, we've calculated that in class before. It's how much you traveled in the end per time elapsed. So for example, if you're going to drive down to Florida, maybe it's 1,000 miles. So you would have 1,000 miles of displacement in the end between here and Florida, and let's say you do that in 15 hours. So you can see the unit analysis here. We end up with miles per hour. Our average velocity would be 66.666 miles per hour. Now, of course, you understand that you weren't always going that speed. Sometimes you might have been going 67, but certainly no faster than that. As sometimes you were going 0, maybe 5 or 10, and all these different miles per hour. But on average, when all was said and done, you just took your displacement, which was 1,000 miles, distance between Utica and Florida, and divide by the travel time. Okay, and that gives you your average. This is actually the slope of a secant line, as we talked about earlier. We have 2 data points, Utica and Florida, time, starting time, ending time, that's 2 xy combinations, and we simply take delta y over delta x, change in y over change in x, change in position per time of change. All right, let's move on. Instantaneous rate of change is at a moment when the camera takes your picture, how fast are you going? That's instantaneous, in an instant. Well, we've already seen that the slope of the tangent line is actually the rate of change at that moment of time. That's the slope of the tangent line. So here is something that you need to memorize. If you're given position and you take the derivative of position, you have just found the velocity function. The function, the machine that will tell you all the velocities at any given time. So if we know where we're at any given time, we can figure out how fast we were going at any given time. So that's pretty cool, and it's thanks to the derivative of position. So velocity is the derivative of position. And in order to find instantaneous velocity, we cannot find the slope of a secant line. We have to find the derivative and plug a number into the derivative, and that'll give us the instantaneous velocity at that t time value. All right, let's move on. We might be asked to find the average velocity between time equals 2 and time equals 5. Well, graphically speaking, that is the slope of a secant line is average, because you're going to find your delta position over your delta time, your change in time, and you'll have your answer. So the displacement here was, look at the numbers, 350 to 50. The displacement was 300. And the time that elapsed was 3 seconds. So 100, let's say miles per I guess I said seconds. That's pretty fast, but let's go ahead and go with it. 100 miles per second. Maybe it's some sort of asteroid screaming through space. Who knows? All right. Now, to find the instantaneous velocity, we would need to actually find the slope, show the slope of a tangent line. Now, in this case, we don't actually have the function, so we can't take the derivative. So please listen carefully on how you do this, because this is new. If you don't have anything else, if you don't have the function, the best you can do for instantaneous would be to find this secant line, to find that secant line that straddles it, because you can see that this secant line is about the same slope as that one. So R apparently is at about 700, whereas point P was at 2, 50. So we could estimate, this is an estimate of the instantaneous velocity, by the way, at 700 minus 50, all over 7 minus 2. So that's 650 divided by 5, which is 130 miles per second. Now notice that that number's higher than our average. Does that make sense? Well, yeah, look at this. This secant line that we first did isn't as steep as the tangent. We are getting faster and faster because our slopes are getting higher and higher and higher in value. So we are what's called accelerating. Okay, over time we are accelerating. Between 2 and 5 we had an average of 100. But at 5, we could estimate, this was an estimate because we didn't actually know what the position, the red position function was. We're just guesstimating. We found the slope of the straddling secant. Nice little alliteration there, a straddling secant. That's just a word I made up, basically. But it's the only way to estimate the slope of the tangent, because you cannot make up data. You can't make up data. We had 3 data points, so we had to use those to find these 2 answers. All right, let's go through this problem. And we have an object that is moving along a number line. It's a position function. S of t is the square of time. So let's start by filling in a little bit of a T-chart here, just so we can wrap our head around what's going on when time equals 0. We are at 0. So in other words, we're starting at the origin, or at 0 on this number line. This is the start, is at 0. Then after 1 second, where are we? After 1 second, we are at 1 on that number line that I've drawn. After 2 seconds, we are at 4. After 3 seconds, we are at 9 on that number line. And after 4 seconds, we're all the way over to 16. You can see we're accelerating. And what do I mean by accelerate? Well, let me try to illustrate it here. So we start here, and then it's 1001, 1002, 1003, 1004. You see how we started bouncing faster and faster as we went to the left. Let me do that again because that was fun. Here we go. 1001, 1002, 1003, 1004. Every second we actually jumped more and more. So what that means is we are accelerating. We're going to talk about that here in a second. So what is the meaning of S of 3? It means that we are at 9 after 3 seconds. What is the meaning of V of 3? That is the instantaneous velocity at t equals 3. So we would actually have to figure out the derivative here, or use the straddling the points a little to the left, a little to the right. So if we're going to find the instantaneous velocity here, we're going to use this data point and this data point. So it would be roughly, this is roughly 16 minus 4 all over 4 minus 2 equals 12 over 2 equals 6 units per second. 6 jumps per second. So at around 3 seconds, we were going at a speed of 6 jumps, or 6 hash marks per second. 6 hash marks per second on that number line. Okay, so that's what that is. And then average velocity over the first 3 seconds would simply be 9 minus 0 all over 3 minus 0, which would be 3 hash marks per second. That was the running average over the first few seconds. All right, a lot to digest here. Hopefully my little animation helped a little bit, and it was, it was fun for me, which is really all that matters, right? Okay, let's move on. There's still more. Speed. Speed is not only a drug that you should stay away from, but speed is a lot like velocity. When you have this object traveling across the board, let me grab the object. It has a certain speed. And actually, I'm going left to right, trying to maintain the same speed. So this might have a speed of 2 centimeters per second. Either way it's going. 2 centimeters per second. So with regard to speed, direction does not matter, because in velocity you can have a sign. Velocity can be positive or negative. However, speed is always positive. Always positive. You don't care if you're going north or south. You just want to know how fast were you going. Earlier in this presentation, I was talking about velocity and how it was increasing. Velocity was going up, and I called it acceleration. So it was changing velocity, how fast velocity was changing. Well, we've learned that the derivative actually tells us how something is changing, how much it's changing, how steeply the curve is increasing, for example. So it turns out if you have velocity and you take the derivative of it, you will actually have the acceleration function. The acceleration tells you how much velocity is changing at a certain moment in time. Like maybe you're increasing by 5 miles per hour every second. That's acceleration. If you imagine yourself at a stop sign and you start going 5 miles an hour faster every second, For the first second, you'd be going 5, and then after the second second, you'd be going 10, and after the third second, you'd be going 15, and so on. And you're going faster and faster and faster because of acceleration. Now, the description that I just gave was actually an acceleration function where you were going 5 units of velocity every time faster. So positive 5 every second, 5 faster, 5 miles per hour faster every unit of time. So in my example there, would have been a of t is 5t. Hopefully you, at this point in your educational career, are all aware of gravity. Gravity pulls you toward the center of the earth. Well, it's actually acceleration. You are being accelerated toward earth. It's this constant pull. So this is called the acceleration due to gravity is called the Freefall Constant. And on earth, it is 32 feet per second squared. And on using the metric system, it would be 9.8 meters per second squared. All right, so we'll see how that's used in the next problem. A general position function of any object in motion on Earth, or actually on any planet, like the moon, or the moon's not a planet, but the moon or Mars or anywhere like that, as long as you have the g for the planet you're on, this is the way this works. On Earth, you would have negative 16 t squared plus v naught t plus s naught. Okay, and do you remember what v naught means? It is your initial velocity. And then what about s naught? So remember, we're using s for position. So this is your initial position wherever you're starting. So I think we've done problems before where, like, you're up on an upper deck and you maybe throw a ball down. Whatever this height is, you might be up 300 feet. That would be your s naught in this problem. And if you toss it upward with an initial velocity, that would be your v naught in the problem. And then gravity takes over, and gravity does the rest and eventually accelerates it toward the ground. One subject that I really find fascinating is economics, which is why that was one of my majors in school. Here we have the concept of derivatives in economics, where c of x could be what we call a cost function. So here's an example cost function. And the way we would describe that is that this is the number of dollars it takes to produce X number of products, iPhones or whatever you're talking about. So if you want to produce 1,000 iPhones, you run it through this machine and it'll tell you the total cost it would be to do that. All right, what do you think R of X means? Hopefully you're thinking revenue. Revenue, this is how much revenue you could expect to pull in by selling X number of iPhones or whatever it is you're producing. So here's an example function. All right, so there's an example revenue function. Now in economics, you can take the derivative of these functions and you get something very special. C prime of x would be 3x squared minus 12x plus 15. And then down here, if you take r prime, you get 3x squared minus 6x plus 12. Okay, now what do these things mean? Well, listen carefully, because this is a bit tricky at first. This function is called marginal cost. Marginal cost. Remember, the derivative tells you how much this guy is changing at a certain spot. Right? That's what a derivative does. It's a slope of a tangent line or a rate of change. So we're wondering how much is cost changing when we produce X units. So earlier when we said 1,000 iPhones or something, you would run 1,000 in here And this will actually tell you how much it would be to produce one more unit. One more unit. Okay, so that's the slope of the tangent line at x equals 1,000 would be the cost to produce one more unit, given that you're already producing 1,000. So really we're talking about the 1,001st unit would be the marginal cost. Okay, if we plug 1,000 in here. Now down here, revenue, it's the same idea. Let's say we're producing 1,000 units. We plug that number in here, we're going to get a number. That's called marginal revenue. That would be the revenue we would expect to receive from that additional 1 unit. All right. Now, what do we use all this for? In the business world, we're often concerned about making a profit so that we can pay ourselves or pay the employees even. Profit is the amount of money you make, take away all the costs you have to pay out. So hopefully this is positive. That's called a net profit. If it would be negative, that's called a net loss. All right, so let's think about the derivatives then. This would be marginal profit is what that's called. Marginal profit is marginal revenue minus marginal cost. Well, what if marginal revenue is bigger than marginal cost? This number will be positive. Should we make the unit then? Should we go ahead and make that 1,001st unit if marginal profit is positive? Well, yeah, duh, we're going to make money on that unit. We're going to make a profit on that unit. So what you do is you just keep producing more and more until marginal revenue equals marginal cost. This is your sweet spot for operating on a business. This is when marginal revenue equals marginal cost, so you're not making any more profit on that next unit, so you might as well not make it. Now, you'll still make profit on all those previous items you produced. We're just talking about that 1,001st unit and trying to make the decision whether we should produce more or not. Okay, so that's how you find the best spot for your factory to produce is by setting marginal revenue equal to marginal cost. And this will be on the AP exam. They expect you to know that this is the best spot to operate on a business. So let me just rehash it one more time. You're given a cost function. You find marginal cost by taking its derivative. They will give you a revenue function. You take the derivative, and that's called marginal revenue. Profit is revenue minus cost. Notice I put it in brackets for a reason, because remember, you'd have to distribute this minus sign on everything in there. And then the same thing down here with marginal profit. It's marginal revenue, take away. You got to put this in parentheses so you can distribute that minus sign. Marginal revenue minus marginal cost gives you how much profit you will make on making that next unit, given that you're already at a certain level. And your sweet spot for operating on your business is where marginal revenue equals marginal cost. All right, there are many applications of calculus in the real life, real world, especially the business world. I had a friend of mine in college who was a business major, and he ended up dropping out of business because he had to take calculus, and boy, he had a rough time. I tried to tutor him as best I could, but there are derivatives in economics, derivatives in physics, chemistry. Everything in the world is always changing, and we have to make decisions, smart decisions, to optimize things. You know, the biggest or the smallest, whatever. That's where calculus can play a role. All right, good luck on your homework. Be sure to bring in questions for Mr. White to go over. Good luck.